Hi everyone, in this video we're going to cover the last part of topic 8 and we're going to talk about breaking the octet rule. So last time we walked through all of these examples on how to make Lewis structures, and one of the primary steps that you learned is that all of your atoms need to follow the octet rule. Well, that's actually not true, so we're going to spend this entire time talking about why that's not true and which atoms to look for that actually break this octet rule and why, and how we can make Lewis structures that break the octet rule. So if you remember, there was one exception that I've already given you, which was hydrogen. So hydrogen is an exception to the octet rule. We saw that it only had one bond, i.e. 2 electrons max around it. So it'd have some other atom here attached to it. And we also had this, you can't add lone pairs to hydrogen. There are other atoms that sometimes don't accept lone pairs. And this is one of those atoms that is okay without forming an octet. So let's explore some other atoms that do similar things. So there are certain atoms on the periodic table that can have less than a full octet. These are your really lightweight and small atoms. So these are small, lightweight, and they're at the top of the periodic table. At top of your periodic table. So they're going to be at the very beginning. So hydrogen, lithium, helium, beryllium, and boron. These atoms are stable with less than a full octet, so less than 8 electrons total. Now, there are some atoms that do always follow the octet rule. They're very strict about this. And that is carbon through fluorine. These are the only atoms that strictly follow the octet rule on the whole periodic table. That's only like 4. So you can see why it's important we talk about this. Because most atoms on the periodic table can break the octet rule, except for these few that strictly follow octets, our octet rule. Okay. Now, as we go down, so we've got our lightweight ones, then we reached carbon through fluorine, we're going to go down into row 3. So as soon as we get into row 3 of the periodic table, anything in that row can have more than an octet. So they can have more than a full octet. So we often see this on atoms like sulfur, phosphorus, and chlorine. Those are going to be examples of things that you'll see a lot. So that means they can hold more than 8 in their valence shell. And sometimes they do this to be more stable. So these small ones will have less than 8. So the small ones have less than 8. Our strict ones that follow the octet rule have exactly 8, and then more than 8 electrons can be in ones that have more than full octet. That being said, atoms that can have more than full octet don't always. So these heavier atoms, these big ones, they can break the octet rule, but they prefer not to. So if they can get an octet, it is ideal. If they can't get an octet and optimize their formal charges, then sometimes they will expand their octet in order to get more. So they'll have an octet if they can maximize or minimize their formal charges. Otherwise, they might expand to more than a full octet. So let's take a look here at exactly how comprehensive this is. So we had said that these atoms here, these guys right here, these small ones, they have less than a full octet. Than 8. So they'll have less than 8 electrons. They're happy with that. Okay? So like helium, for example, here. Helium, it will have 4 electrons. It likes to have 2 valence, so it usually likes these 2 valence right here. But that means that it will have 4 electrons, and it's quite happy with that. Lithium as well, less. Boron, we've seen an example of boron where we have hydrogens around it, like this. This one's happy with 6 electrons. It wants 3 valence. It's in group 3A here, so it likes to have 3 valence. That gives it a formal charge of 0. But if we notice, it only has 6 in its octet, and it's pretty happy with it. It's stable there. Now, our atoms that strictly follow the octet rule are carbon through fluorine right here. That's it. That's literally it on the periodic table. These are the ones that never, ever, ever, ever break the octet rule. Never break octet rule. Everything else on the periodic table is fair game. So all of these other ones down here, row 3 and beyond. All right, to infinity and beyond. These guys, they can break the octet rule. So they can exceed 8 valence electrons. So they can have more than a full octet. Now again, they don't always have more than a full octet. If they can keep an octet and have the best formal charge, they will do that. But if their formal charges aren't very good, then they will expand their octet. Okay, so question for you. Based on what we just learned, which atoms on the periodic table always follow the octet rule, no matter what, and cannot break it? So we had learned previously that was these 3 right here, carbon, or 4, carbon through fluorine. Those are the ones that never ever break octet rule. Okay. It's important to remember because a lot of compounds, especially organic ones, are made of carbon through fluorine. The only other thing that might be added to an organic molecule might be your hydrogen here, which is the only one that wouldn't follow an octet in a structure like that. Okay, so now let's work through an example. So I'm going to ask you to draw a Lewis structure of a molecule that does not need a full octet on its atoms. So we've already done BH3, I already showed you that example, so we're going to do something else. Let's look at BeH2. So that's here, that's this beryllium here, and this hydrogen here. So see if you can use our Lewis structure rules in order to make this Lewis structure and find out how many bonds are on each atom here. Remember, you'll need to choose your center atom, you'll need to make your skeletal structure, and then you'll need to total your electrons, make sure you have enough electrons in the molecule, check the formal charges, and because this does not follow the octet rule, we are not concerned about that for this molecule. Let's take a look at how to solve this one. So in order to figure out which atom is our central atom, we need to look at electronegativity. Beryllium has an additional electron shield as you go down the periodic table, so it's definitely less electronegative than hydrogen. So it's going to be at the center here with our hydrogens on this side. Let's see how many total electrons we have in the structure. So beryllium is in group 2A, so it's going to contribute 2. So we'll have 2. Hydrogen is in group 1, it's going to contribute 1, but we have 2 of them, so plus 1, plus 1. So total, we're going to have 4 electrons in the structure. All right, so let's go to the structure and place those. So right now, in the structure, we have 1, 2, 3, 4 total electrons. So we can't add anymore. We're done. Okay. Another thing to notice as well, if we calculate formal charge, so beryllium wants 2. It has 2 electrons. So it's got these 2 right here. 1, 2. So its formal charge is 0. Hydrogen wants 1 because it's in our group 1. It has 1 in its valence shell. So its formal charge is also 0. Same with this hydrogen. It wants 1, it has 1, it's 0. So our formal charges are all optimized. This is the best structure that we can get here because our formal charges are as low as they can go. So the only thing wrong with this is it doesn't follow the octet rule, which we've said is okay for these lightweight atoms. So this is the structure, the correct structure for beryllium with the 2 hydrogens attached. Now let's try doing one that has an expanded octet. So chlorine trifluoride I'm going to ask you to draw the Lewis structure for this and see how many bonds are on each atom in this molecule. So how many bonds are on the chlorine, how many bonds are on each fluorine, and how many lone pairs are on each of the atoms. How many lone pairs are around the chlorine, how many lone pairs are around the fluorines. Okay, all right, so here's chlorine, here's fluorine. Remember your steps, find the central atom, count the total electrons, and then you can check your octet rule if you want. We know we're going to break it this time. Again, it's not always broken, but you should see it in the structure, I think. And then check your formal charges, okay? Let's take a look at how to solve this one. So we need to figure out which of these atoms is less electronegative. It's going to go in the center of our molecule. If we look, we've got fluorine in row 2, chlorine in row 3. Chlorine's going to have another electron shield, so we definitely know it's less electronegative. Also, fluorine is the most electronegative atom on the periodic table, so it's definitely less. So we're going to put chlorine at the center. We're going to put our 3 fluorines off to the side. Okay, let's check how many total electrons we want in the structure. So fluorine and chlorine are both in group 7A. They all want 7. So chlorine is going to contribute 7, and our fluorines are going to contribute 7 as well. So plus 7, we're going to add 3 of those, which gives us a total of 4 7s. So 4 times 7 is 28. So we have 28 electrons to place. So let's take a look at our structure, see what we already have and what we need to add. 1, 2, 3, 4, 5, 6 is what we already have. So that means we need to place 22 more electrons around here. We're going to start on our outer atoms, remember, and work our way in. So we're going to fit a full octet on our exterior atoms. So right now they only have 2. So that means we go 2, 3, 4, 5, 6, 7, 8 around this fluorine. 2, 4, 5, 6, 7, 8. 2, 4, 5, 6, 7, 8. Let's see how many electrons this is total. 8 times 3 puts us at 24. Am I right on that? So let me recount these in a way that makes a little bit more sense. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So now we've got, we've added 18, this 18 electrons. So we have 4 left. We have 4 left to place. They've got to go somewhere. So if we filled our octets on our exterior atoms, and the octets on our exterior atoms aren't being broken, they can't be broken, then we have to place these electrons on our interior atoms. So these 4 electrons have to go on chlorine. So they've got to go on the center. So we're going to do that. We're going to put them in the center here. 1, 2, 3, 4. Okay. Now that looks really weird, right? Okay, so we've got 4 electrons. Remember, electrons come in pairs, so you don't want to place them as 1, 2, 3, 4. You want to place them together as pairs. Now, let's check our formal charges. So we've got all of our electrons on. We're going to ignore the octet rule for the minute on chlorine because, again, it's going to break it in this one. So for fluorine, fluorine is in group 7A, so it wants 7 electrons, valence electrons. Let's see how many it has. It has 7. Let's take a look at this other fluorine. It's going to be the same thing. 2, 4, 6, 7. 7 minus 7 is 0. Same with this one here. 7 minus 7 is 0. So fluorine's quite happy. Let's take a look at chlorine now. Remember, you can always add double bonds or triple bonds in order to fix stuff if you need. So chlorine, we've got 2, 3, 4, 5, 6, 7 electrons. We have 7. Let's see what's up here. It wants 7 as well. So 7 minus 7, 0. So our formal charges are all optimized for this one. If you had put a double bond on one of the fluorines or something, you'd find that you can't actually fit all of the electrons on here. And you would have to have like 3 lone pairs on the chlorine, and then your formal charges wouldn't work out as well. So you could have tried something like this. I think you could have done something like this. Fluorine, put another lone pair here, and then fluorine. You could have tried something like that, but you would end up not having the right formal charges. So this might be another alternative structure here if you were trying to put double bonds on here to kind of like help balance it out. So let's see why this structure is wrong. Whenever we go to check our formal charges right here, fluorine wants 7 and would have 6, so that would give it a formal charge of +1. And if we went to our chlorine, sorry, that's a chlorine, we'd circle this, it'd have 2, 3, 4, 5, 6, 7, 8, 9, 10. It would have 10 electrons around it. It can do that. It can expand its electrons. So it would have 10, but it wants 7. So it wants 7 minus 10. That would give it a charge of -3. Holy moly. Okay. So that's really high. Most of the times, formal charges, you're only going to see like a 1 at most. Sometimes you might see a 2, but it's pretty rare. You'll see +1 and -1 and zeros the majority of the time. So -3 is like really out there. That's definitely wrong. All these other ones are pretty happy right here. 7 minus 7 is 0. 7 minus 7 is 0. Oops, -7 is 0. But you can definitely see that formal charges are best in our original structure. And there's less electrons even around the chlorine, even though it does break the octet rule. So as we saw in the last example, for atoms that break the octet rule, they add electrons until they achieve the formal charge they want. So they won't add electrons to form an octet. They'll add electrons until they're electronically stable. So what we call this tendency to add electrons, like how the chlorine did, we call this hypervalency, or you might hear me call it an expanded octet. So this here, let's say this is our chlorine, and these are our fluorines around here. You can take this same structure with chlorines and fluorines, fluorines and fluorines, fluorines. And let's say this is a lone pair here. So they can expand their octet essentially. So they'll take it from like a tetrahedral structure and they'll add another lone pair and they'll even change their geometry. So their structure looks different when they add these lone pairs on. So you'll see it go from something like this to something like this, even though it contains all the same atoms. So we still have 1 chlorine and 4 fluorines, but as soon as you tack a lone pair on there, they rearrange in their 3D space to allow for that lone pair to exist. And this is what we call hypervalency or an expanded octet, because that chlorine is allowing more electrons to attach to it and break the octet rule. So that's it for learning how to break the octet rule and incorporating those into Lewis structures.